Morning, students. Last class we have completed extra shortest path routing algorithm. After that, we have discussed about the flooding algorithm. Okay, today we are going to start the next algorithm, that is a dynamic routing algorithm named distance vector routing algorithm. This algorithm is also known as Ford-Fulkerson routing algorithm. Ford-Fulkerson routing algorithm. Here, in this algorithm, each router will maintain a routing table. Each router will maintain a routing table in order to give the best known path to each destination in which the line to use to go there. Here, these tables are exchanging the information with the neighbors. Just simply you can remember, in this routing table, each router will maintain a routing table. Okay, that routing table is mainly for will give us the best known distance to each destination. Okay, just simply you remember this point. Okay. Next, coming to this algorithm, here we are having two contents. One is table content and second one is table updating method. Coming to table content, in distance vector routing algorithm, each router will maintain a routing table index. Routing table indexed by and containing one entry, each router in the subnet. Okay, I will show you in the diagram. Okay, I will show you in the example. This is the example for distance vector routing algorithm. Just take a pen and paper and note it down and take a screenshot of this clip also. Here we are having a subnet which is containing the routers A, B, C, D, E, F, G, H, I, J, K, L. These are routers. Here we have taken an example. Just see my cursor point. We have taken an example, router J. Okay. In this subnet is containing nodes or routers. A, B, C, D are nodes or routers, and I have taken in this example router J. Okay, the delay from router J to all its neighbors. The delay, that means the distance from J to all its neighbors. What are the neighbors to J here? The neighbors are J is connected to I is one neighbor. J is connected to K is one neighbor. J is connected to H, that is one, and J is connected to A. Here they have given the distance. I have taken the example J to all its adjacent nodes I, K, H, and A. The distances they have given here. JA. The distance between J to A is given as 8. The distance between J to I is given as 10. The distance between J to H is given as 12. The distance between J to K is given as 6. Here they have given JA delay. That means the distance between J to A, J to I, J to H, J to K they have given. Okay. Now, what we need to do here is, this is the routing table for A. This is the routing table for I. J is connected to I, K, H, and A. The routing tables for A is given, I is given, K and H are given here. Okay. These are the weights. Just we have to take our own. And from these four tables, A, I, H, K, from these four tables, we need to derive the routing table for J. This is the new routing table for J according to these tables. Okay. Just remember clearly, students. First, I have here a subnet. I have here a subnet containing the routers A, B, C, D, E, F, G, H, I, J, K, L. And the second diagram is containing, see here the points they have mentioned, show that delay vectors received from neighbors of J. Delay vectors received from neighbors of J. Neighbors of J are I, K, H, and A. They have given. Suppose that J has measured or estimated its delay to its neighbors. Here we need to measure. J has measured its estimated delay from its neighbors A, I, H, K. A is 8, I is 10, H is 12, and K is 6. These are the estimated delay or estimated distance from J to its neighbors. From these neighbors routing table, we need to draw the new routing table for J. Okay, let's take an example. Here, this is the routing table for A, for I, for H and K. Okay, for routing table, these are the destinations A to A, A to B, A to C, A to D, and so on, A to L. Here we know some values. A to A we know the value is 0, and JA delay they have given. The estimated delay between J and A is 8. See here, JA is 8. Here, see here. This is 8, not 9. JA is 8. Okay. Next. These are the weights just we have taken with our own. Okay. These values, all these values are our own. In this table, only 2 weights. A to A is always 0. So JA, that means the distance between A to J is, this is not 9 students, this is 8. Here it is 8. Okay, all we have taken our own. Okay, now JI, this is ith routing table. I to I is 0. Here this value I to I is 0, and JI also given it is 10. JI also given it is 10. Okay. Here we have taken old value. Sorry, students. This is the old value. This is the old value, and this is the old value. And in this routing table, H to H is 0. The rest of values are we have taken our own. In this routing table, K to K is 0. The rest of values we have taken our own. Okay. I'm repeating once again, students. We have 4 routing tables which are adjacent neighbors to the router J. The first router is A. In A's routing table, A to A to B, A to C, A to D, A to E, A to F, A to G, H, I, J, K, and L. In those values, only we know one value. That is, we have to take A to A is 0, and all other values we have taken our own. This is 9 students, not 8. This is 9. We have taken our own. Okay, we have taken our own all these values. And in the ith routing table, I to I is 0. The rest of values will be our own. In the H routing table, H to H is 0, and the rest of values are our own. And K to K is 0. The rest is our own values. Okay. From these routing tables, we need to derive a new estimated delay from J. That means J's routing table. Okay. Here you need to listen carefully, students. What is this routing table? This is the routing table for J. This is the routing table for J. That means J2A, J2B, J2C, and so on, J2L. Okay? Yes, you remember like that. First, J2A. J2A, they have given what is the value? 8. J2A is, they have given here, see here, J28 delay. See here, suppose that J has measured or estimated its delay to its neighbors A, I, H, and K are 8, 10, 12, 6 milliseconds. See here, the delay will be 8 here. Now, J2B, this is J2B is 20. How this 20 will come? How this delay will come? Suppose our source is J, our destination is B. Source is J, destination is B. Okay, to go from J to B, we need to go for J to K and K to B is one route, J to A and A to B is one route, and J to H and H to B is one route, and J to I and I to B is one route. Okay, just listen, students. First, we will check the values. Take the pen, students. Take the pen and paper. First, we will calculate J to A and A to B. A to B value we know here. A to B we know here. J to A, what is the value for J to A? 8. And A to B. A to B value is 12. 8 plus 12. What is the value? 20. Okay. The first possibility is to go from J to B. The possibility is J to A and A to B. J to A delay we have given 8 and A to B value we know here 12. 8 plus 12. What is the value? 20. Okay, this is the first value. Now to go from J to B, the second possibility is I. J to I value is 10. I to B value is 36. I to B value is 36. 36 plus 10, what is the value? 46. To go from J to B through I is 46. Okay, this is 20. The second one is 46. Now third one. To go from J to B, the alternative is H. J to H is given 12 and H to B is given 31. 31 plus 12 together 43. 20, 46 and 43. And next, the another alternative is J to K and K to B. J to K they have given as 6 and K to B they have given as 28. 28 plus 6 is 34. This is 20, this is 46, this is 43 and this is 34. The least value in this is 20. So J to A will become 20. The line will be A. That means to go J from B, the line will be A. Okay. Similarly, J to C. J to C. First, J to A is 8. A to C is 25. That is 33. The value is 33. J to I is 10. And I to C is 28. Sorry, 18. 18 plus 10 is 28. And J to H is 12 and J to C is 19. The value is 31. Here the value is 36 plus 6, 42. The least value, this is 33, this is 28, this is 31, and this is 42. The least value is 28. That is, to go from J to C, the line will be I. See this one, J to I and I to C. The value is 28 and the line is I. Now, J to D. J to A is 8. A to D is 40. That is 48. J to I is 10 and I to J to I is 10 and I to D is 27. 27 plus 10, 37. 8 plus 12, that is 20. Next 24 plus 6, 30. The least value is 20. So J to D is 20 and the line is H. Okay. Next J to E. J to A is 8. A to E is 14. 14 plus 8, 22. 7 plus 10, 17. 30 plus 12, 42. 22 plus 6, 28. The least value is 7 plus 10, 17. To go from J to E, the line will be I and the distance will be 27, sorry, 17. Okay, here the value is 7 and this one is 10, that is 17 and the line will be I for J to E. Next, J to F. J to F, here 23 plus 8, 31, 20 plus 10, 30, 19 plus 12, 31, 40 plus 6, 46. The least value is 20 plus 10, that is 30. The line will be I. Okay, similarly, we need to check the rest of values also. This will, here J to J is 0. The J to J is 0. These are the lines. The lines will be A, I, H and K. Why? Because the adjacent routers, the adjacent nodes for J is H, K, A and I. Okay. This is the new routing table. This is the new routing table. Here in this distance vector routing algorithm, these values, just you can take, I have taken here J. You can take any other router or node and just you can find out the adjacent nodes and you can find out the all delays from that router to adjacent nodes they have given here, and all these values are our own values except from A to A, I to I, H to H and K to K, all are our values. From these tables and the estimated delays, these are the estimated delays from J to its adjacent nodes A, I, H, K, and from these two figures, from these 2 points, I have derived here the new routing table, the new estimated delay from J to all other nodes, other routers in the table, and this is the lines through which they have gone through. Okay, this is the new routing table for J. This is the distance vector routing algorithm. The main disadvantage of this distance vector routing algorithm is the maintenance of routing table. See here how many routers we are having in this table. Here we have 1, 4, 8, 12. So each table is having 12 entries in the routing table, and we are having 12 routing tables into 12 tables, total 144 entries. These 144 entries needs to be maintained in the main memory, is in the main memory. Okay, here the memory needs to be wasted, memory will be wasted. Okay, in order to cover this problem, the major disadvantage is we need to maintain a routing table for each router. The entries will be the total number of nodes. Here the total number of nodes in is 12. In each routing table, we are having 12 entries. Hope you understand, students. Just take a screenshot of this one and just you can practice. It's very simple. You can take your own values here. I have taken J as example here. Okay, this is the distance vector routing algorithm. This is dynamic routing algorithm because the routing decisions may be changed. The routing decisions may be, see here, initially here we are having J to A is 8 here. Sorry, J to A is 0 here. Now the J to A becomes 2. Sorry, the values will be changed. J to J, see, A to J is 9. Here 8. Here J to J's routing table, right? J to A, what is the value? 8. Here the value 9. That means the routing decisions may be changed. The routing decisions may be changed. In the static routing algorithm, the routing decisions do not change. In this dynamic routing algorithm, the routing decisions may be changed and the routes also changed. That is the reason why it is said to be a dynamic routing algorithm. Okay. It's about distance vector routing algorithm. I will tell you the link state routing after. First, we need to know the hierarchical routing algorithm. This hierarchical routing algorithm is an improvement for distance vector routing algorithm. Here, in this routing algorithm, the routers are divided into regions. The routers are divided into the regions. Okay. With each router knowing all details how to route the packets to its destinations. Okay, here the major responsibility of the router is will maintain a routing table, and each router knows all details how to route the packets to the destinations. Okay, in huge networks, in the previous example we have seen a small network, right? This is a small network. Only we are having 12 routers. In real time, we are having huge networks. And here in this example, here two-level hierarchy may be insufficient. Two-level hierarchy may be insufficient. It may be necessary to group the regions. I will show you in the example how. This is the example. See here. Here the routers, here the routers 1A, 1B, 1C. These three routers are grouped into a region 1. These are comes into the region 1. Here we are having 5 regions. In the region 1 we are having 3 routers, 3 nodes. Region 2 we are having 4. Region 4 we are having 2. Region 4 3. Region 5 we are having 5. Okay, just total how many? 3 plus 4 7 plus 2 9 plus 3 12 plus 5 17. That means in this example, in this we are having 17 entries. 17 entries in each routing table. 17 into 17. That means at each router we are having one routing table containing 17 entries. For the same will be for the total 17 routers. Okay. That is the previous case. Here we are having, this is the this is the full table for 1A. Just I have taken an example. 1A's routing table. 1A in the region 1. 1A's routing table will be like this one. 1A to 1B, 1A to 1C, 1A to 2A, 2B, 2C, 2D, 1A to 3A, 3B, 4A, 4B, 4C, 5A, 5B, 5C, 5D, 5E. Total altogether 17 entries for 1A table. 1A, this is previous example. That means previous model. See, for 1A to 1A, the line will be 1, the hops will be 0. 1A to 1B. 1A to 1B we are having, this is the, see, this is the destination, the line and the number of hops. 1A to 1B. There is a direct line. The line will be 1A, 1B and the number of hops. 1A to 1B. The hop means this is one hop. Okay, the line between two nodes is measured to be one hop. HOP hop. 1A to 1C we are having direct line, that is 1C. 1A to 2A, 1A to 2A, 1A to 1B, 1B to 2A. That is 1A to 2A, the line will be 1B, the hops will be 1 and 2. Okay, next 1A to 2B. 1A to 1B, 1B to 2A and 2A to 2B. The hops will be 1, 2 and 3. the line will be 1B. See here, the hops will be 3 and the line will be 1B. 1A to 2D, 1A to 2D, 1A to 1B, 1B to 2A, 2A to 2B, 2B to 2D. The hops will be 1, 2, 3 and 4. The line will be 1B. See here, 1A to 2D, the line will be 1B and the hops will be 4. Now 1A to 3A. 1A to 1C, 1C to 3B, 3B to 3A. To 1A to 3A, the hops will be 1, 2 and 3. The line will be 1C here. The line will be 1C here. Similarly, 1A to 3B, 1A to 1C, 1C to 3B. Line will be 1C and the hops will be 2. Like that, we need to calculate 4A, 4B, 4C, 5A, 5B, 5C, 5D, and 5E. Okay, this is the normal routing table. Okay, for this given example, we are having 17 nodes or 17 routers. Each table needs to maintain 17 entries. 17 into 17. What is the value in 17 into 17? Here in the previous example, 17 into 17 will become 289. 289 entries. Okay. In the previous example, how many entries here? Here 12 into 12 into 12, 144. 144 entry, total entries are 144. In this, we are having 17 into 17, 289 entries. So that to maintain 289 entries, it will become a problem. So that we have divided these nodes into regions. Per region, first, this is the hierarchical table. For 1A, the hierarchical table will be, see, this is the right side one will be the hierarchical table for 1A. 1A to 1B, 1A to 1C. See, 1A to 1A, 1A to 1B. See, 1A to 1A, the line will be 1A to 1A, the line will be nothing, hops will be nothing. 1A to 1B, the line will be 1B and the hops will be 1. 1A to 1C, the line will be 1C and the hop will be 1. 1A to 2, 2 means the region 2. 1A to 2, that means region 2. 1A to 1B, 1B to 2A, 2, right? So the line will be 1B, the hops will be 1 and 2. See here, line will be 1B, the hops will be 2. 1A to 3, the region 3. 1A to 1C, 1C to region 3, right? So hops will be 1 and 2, the line will be 1C. 1A to the region 3 is, the line will be 1C and the hops will be 2. 1A to region 4, that is 1A to 1C, 1C to 3B, 3B to 4. That means 1, 2 and 3. The hops will be 3, the line will be 1C. Now 1A to 5. See, you need to calculate from this all possible sides and always you need to take the shortest value. 1A to 1C, the 1A to 1C, 1 hop, 1C to 3B, 2, 3 and 4. 1A to 5, region 5 is 1C and the hops will be 4. Okay, this is the hierarchical table for 1A. In the full table, we are having 17 entries. In the hierarchical routing table, we are having 1, 2, 3, 4, 5, 6 and 7. Only 7 entries for the hierarchical table with respect to hierarchical routing algorithm. Okay, this is reduce the total number of entries in the routing table. So in the memory also it will take less memory rather than the full routing table. Okay, this is here why it is said to be hierarchical routing algorithm means here in this algorithm the regions has been divided. In the when the routing is done hierarchically, this one, okay. This is the hierarchical routing table and distance vector routing table. The hierarchical routing algorithm and distance vector routing algorithm. The distance vector routing algorithm is having the problems of more number of entries to be maintained in the routing tables. The correction, at more improvement is the hierarchical routing table. In this, the routers are divided into regions, and we need to draw the hierarchical table instead of full table for each node or router. Okay, this is in the tomorrow's class. We are going to start the next routing algorithms. That is link state routing algorithm and broadcast routing algorithm. Okay, that's it for today, students. Wait for a while. Someone will take the attendance. Thank you, students.